Gravitational waves have long been suspected in 1916 after Einstein's final conception of the field equations of general relativity. A set of linearized weak field equations hosts a wave solution of transverse perturbations of spatial strains propagating at the speed of light. And at last, a century later, the LIGO Virgo confirmed the first detection of a pair of black holes merging and radiating an excess mass in the form of gravitational waves, practically confirming Einstein's predictions and opening new avenues for research on gravity, one of which is the notion of a lensed gravitational waves. And with much motivation, we investigate the gravitational lensing signatures in gravitational wave signals from compact binary coalescences. In the geometric optics limit, the trajectory of a gravitational wave may curve due to a massive astrophysical object, and just like light, its lensing occurs in many ways depending on the properties of the lensing mass. Strong lensing occurs for massive lenses, causing magnification and multiple images of the source. Meanwhile, lensing caused by compact objects are called microlensing, characterized by the beating patterns in the waveform of the lensed signals. We investigate the combined effects of strong and microlensing of a gravitational wave signal with a singular isothermal ellipsoid galaxy model and the point mass. We first identify images caused by the galaxy alone, and then we place point mass lenses at the sky locations of the most magnified images, each in the positive and negative parity sides of the galaxy. We generate a gravitational wave signal from a non-spinning binary merger above the advanced LIGO threshold but sub-threshold to advanced Virgo detector. We show that the combined effects of strong and microlensing enhances the amplitude of a gravitational wave signal to surpass threshold limits for both detectors. We also observe beating patterns on the amplitude for both the positive and the negative parity lensing. A more prominent beating is seen on the positive parity of the galaxy. Bulashenko and Ubach found that the beating features of the lensed gravitational wave signals provide a lower bound estimate of the point mass lens in the case of microlensing alone. In our setup, this exceeds the actual mass of the point mass lens by 3 orders of magnitude due to the addition of strong lensing. Well, if you are interested in other outcomes of my study, tara na on January 9, 2023 for my thesis defense. Salamat at kita-kits!